Part A. What probability distribution represents the variable time measured in hours elapsed between two consecutive calls? How much time will elapse on average between two calls? First of all, in this statement, we have been told that the number of calls received daily in 24 hours by a towing service follows a Poisson distribution with an average of 64 calls. Therefore, we define the random variable as x equals the number of calls received in 24 hours. Since the problem says the calls follows a Poisson distribution with an average mean, which is the mean of 64 per day, we can write it as x follows a Poisson distribution with lambda equals 64. Here, lambda equals 64 means that on average there are 64 calls every 24 hours. So here the Poisson model is used because we are counting how many random events in these calls, in this case calls, happens in a fixed period of time. Now, later in part A, they first ask us, which is the probability distribution, what probability distribution represents the variable time in hours elapsed between two consecutive calls. According to this statement, we need to introduce a new variable that we call y. You can call it any other letter, which is the time in hours between two consecutive calls. Whenever the number of events here in its calls in a time period follows a Poisson distribution, then the time between two consecutive Poisson events is a new random variable that follows an exponential distribution. So now the variable y follows an exponential distribution. The parameter lambda, which is the average, is the same for both, but we must express it in the same units as we are measuring the time. So we need to rearrange the parameter lambda, which is 64 calls divided by 24 hours. So we write the exponential distribution of the variable y as y follows an exponential distribution with lambda equals 64 divided by 24. This means that on average we have 64 divided by 24, which is 2.67 calls occur every hour. Finally, we answer the second question, which is how much time will elapse on average between the two calls. So we need to find the expected value, that in an exponential distribution, the expected value equals 1 divided by lambda. So here we substitute the values, so 1 divided by 64 divided by 24, which is 0.37 hours, which is the average time between the two calls.
Any given day, what is the probability that the service will not exceed 50 calls? For this question, we define the random variable x as the number of calls received in 24 hours. Since x represents count data, it follows a discrete probability distribution, specifically a Poisson distribution. We are asked to find the probability of x being lower or equal to 50. Our commander, we select distributions, discrete distributions, Poisson distribution, Poisson tail probabilities. We put in the following values. Variable of the value, 50, mean, 64, and tail, lower tail. The resulting probability is approximately 0.0417, rounded to the 4 decimal places, since probabilities are usually reported to 4 decimals.
Section C. Over the course of a month, on average, how many days does the towing service receive 50 or fewer calls? Now, instead of calls in a day, they're asking us during a period of time of a month, 30 days. We have already calculated the probability of obtaining 50 or fewer calls in a day, being a discrete variable. Then, we will have to define a new random variable, because the calls from day to day are independent events, and each day has the same probability, P, of being a success. The new random variable, W, is the number of days the service receives 50 or fewer calls, and it follows a binomial distribution. Why? Because we have a dichotomous experiment. The call service receives 50 or fewer calls on day. 1 yes and 0 for no. This dichotomous experiment is repeated 30 times independently of the number of calls received on one day is independent from the number received on another day. So we would say n as the number of times we repeat the experiment being 30, and p as the probability of obtaining 50 or fewer calls, being 0.0417, which this number was previously calculated. The expected value of this can either be calculated as the product of n and p, or with the R Commander program, resulting in 1.251 days, and we will leave this result with decimals. This result means that on average, about 1.25 days per month, the Darwin service will receive 50 or fewer calls.
If some of the workers, after receiving the last call, are on a coffee break, what is the probability that they could extend the break for half an hour without any new calls? We defined the random variable y as the time in hours between two consecutive calls. Since the number of calls follows a Poisson distribution, the time between calls follows an exponential distribution. We're asked to find the probability that no new calls occur during the next 0.5 hours. That is the probability of y being greater or equal to 0.5. Air Commander, we select distributions, continuous distributions, exponential distributions, and exponential probability. Then we input the following parameters. Variable value 0.5, rate 64 divided by 24, upper tail. The result gives the probability that the time between calls is greater or equal to 0.5 hours. And the result for this probability is 0.2636. We can conclude that the 26.36% of the times they extend the break half an hour, they wouldn't receive any new calls.